welcome to the Rocket Chip Intensive at the first Chisel Community Conference. My name is Henry. I'm a Rocket Chip developer. Yeah, let's see. So I'm going to give you like a brief overview of what Rocket Chip is and where it came from, and then we're going to get into the specifics of kind of all of the different pieces that make it up. Just as a quick taking your temperature, who here is like used Rocket Chip on a project, or is everybody, you know, pretty fresh to it? Yeah, okay. There's a few experienced users, but looks like mostly new people, which is great. So yeah, I'll give you some backstory. Rocket Chip has been around for a while. I think we started it in around 2011. It kind of grew out of the Chisel project, and it really was actually at the crossover between Chisel and RISC-V. So there were people developing RISC-V processors as part of their graduate student theses projects, and there were people working on Chisel. And you know, based on, and I was a part of this research group, and based on some of our experiences trying to kind of rapidly iterate on prototyping different designs, we started building up these various sort of libraries in Chisel that were helping us be productive in composing larger systems. So there were some people working on RISC-V processor pipelines. I was working on cache coherence protocols and cache controllers. There were people working on vector coprocessors and other accelerators. And so Rocket Chip was sort of the agglomeration of all of those different libraries. Like, let's put all of this together and make a kind of unified chip. So what's on the screen right now is a lineage of different processor designs that got taped out at Berkeley using Rocket Chip over the last 6 years or so. So I was at Berkeley from 2011 through about 2016. So I left right before Hurricane 1. And I currently work at Sci-Fi, which is a company that is selling RISC-V processors and processor IP. And we are continuing to use Rocket Chip, which is open source. And we have extended it internally to add more devices and you know, different peripherals. I'll get into the different ways that Rocket Chip can be extended, but we still continue to support the open source version, and I'm one of the contributors to that open source effort. Now we got back. Okay, so overall what I want to talk about today is sort of like the scope of Rocket Chip, like what is it good for? Then I'm going to talk a bit about the packages that make up Rocket Chip. We have it sort of segmented into different pieces of functionality. Then I'm going to touch on some important APIs that are used within Rocket Chip. This is, you know, it's not going to be kind of an exhaustive list of all of them, but it'll at least touch on, I think, some interesting or useful ones. That, I think, is the part where if you guys have questions about particular ones, we can actually go and look at some source code and be like, what is this doing? And then I'd also like to talk, so, you know, Rocket Chip is sort of now forms the core of a larger ecosystem, and there's sort of some additional external repositories that provide more collateral that can be combined with Rocket Chip to build up even bigger systems. So I'll give an overview of those. And then at the end, I'll talk about sort of some of the projects that we're actively working on within the scope of Rocket Chip and those other repositories. And then that's probably not an hour of content, so I think there's going to be some time where I'm just going to sit here and you guys can ask me questions about projects that you're working on or ideas that you have, feasibility, anything like that. So, and feel free to interrupt me with more questions at any point. I have a lot of backup slides related to some of the more specific topics, so we can always deep dive into any particular topic if anyone wants. Any questions so far? Cool. Okay, yeah, talked about that already. Okay, so these are basically the reasons why I think Rocket Chip is a cool project and what tasks I think it, as a sort of software artifact, it has really sort of taken the lead on and is providing some cool features of. So, Chisel is really good at making you efficient at describing particular circuits, right? You can use either the functional programming or the object-oriented nature of Scala to kind of very concisely express, this circuit is composed out of these register and wire mux primitives, and I've combined them all together in this way. However, for a sufficiently large design, you are really talking about taking sets of modules and combining them into a bigger system. And this is where the stuff that's built into Rocket Chip is really designed to tackle, is I have this diverse set of processors, memory map devices, memories, caches, and I want to combine all of those together to make a complete SoC. So how do I describe the connectivity between all these components? How do I ensure that I've connected these components safely? And can I take advantage of components that other people have written that are providing me with a productive environment to do my prototyping work? So for example, having a cache coherent shared memory system is sort of a nice thing to just get out of the box for a lot of people. So basically, the idea behind Rocket Chip is here we've built up this set of libraries, and we've provided a simple example processor. And the original idea was you can just fork this repository and start building your own processor. Now, what's happened over time is people have actually made sort of even more meta repositories that include Rocket Chip as a submodule and sort of treat it as a library, and then add more IP to it externally. So we'll get to that later, but the initial vision was, this is supposed to be a complete set of stuff that you, resources that you can use when you're building your processor. Okay, what is Rocket Chip not good for, or at least not yet? So actually the second issue that was ever opened against the repository when we open sourced it was a graduate student who said, hey, I checked this out, and I set the number of processor tiles to 100, and it didn't work. And I was kind of like, come on, dude. Many core research was really hot then, and our lab had been doing some work on that. But I was like, we did not manage your expectations well here. You really. I'm not saying it can't be done, but out of the box, the processors that are included are fairly beefy. The interconnect that's included is an all-to-all crossbar, so you're not going to fit it on an FPGA. On the other side of the spectrum, we also get a lot of requests that are like, I'm trying to get a minimum viable RISC-V product, on the smallest FPGA I can find. And why are you giving me all of this extra stuff? It's too big, it's not fitting on my small FPGA. And so that's another situation where Rocket Chip, if that's the focus of your project, Rocket Chip might not be a good fit. At this point, there are a lot of very nice kind of minimal Verilog, either FPGA soft cores or even designs targeted for ASIC out there. Not to say you can take Rocket Chip and turn all the knobs down as small as they go, but you might not be as satisfied as you would be with a sort of more single purpose solution. And then the final thing that Rocket Chip is not good at is avoiding having caches. This is partially because I spend a lot of time working on cache coherency stuff. In general, I think caches are pretty useful for a lot of programmers. I'd say the number one issue that gets opened against Rocket Chip right now is how can I take out the caches? Again, these are people who want a smaller design. They're probably more used to an embedded programming environment where they're used to managing their own scratchpad memories. And so we've been slowly trying to add features where you can take out the data cache and replace it with a scratchpad. We've moved things a bit in that direction, but the default out-of-the-box behavior assumes that you want all of your processors to have L1 data caches, and you want a cache-coherent memory system beyond that. Okay. Yeah. Any questions about that?
Yeah. So I mean, I know you said you can't have caches, but is it possible to just scale down the cache to the point where it just keeps?
Yeah. So you can. There are a couple of tricks you can play. You can dial down the size of the caches to be pretty small. You know, sort of in the. I'm not actually sure what the smallest you can successfully make it is, but you know, let's say, you know, less than a kilobyte in size. I think for the iCache you can probably even get it to be just basically a single line prefetch buffer. And so that might, depending on your use case, that might be
effectively disabled at that point.
Yeah, but it really depends a lot on your use case. So if some people are very concerned about, say, like real-time performance guarantees, and so that's a situation where, you know, having a scratch pad that has a guaranteed latency is really what you want. Now, yeah, we could talk more about the set of features that start making Rocket Chip look more and more like that kind of system. The instruction cache can be configured such that basically ways are locked. The data cache can actually now be swapped out for a scratch pad, but you have to have something there in terms of how it interacts with the core pipeline. And so, you know, if really all you want is just a RISC-V processor pipeline, and that's it, Rocket Chip is not really a good fit because it's trying to build up this whole SoC, and so you could build that, and then you could go dig around in there and start trying to rip that piece out, or try to build it as a standalone thing, but it's just not really. You're going to have a lot of friction, basically.
As I remember, one of the issues was that people wanted a soft core on the FPGA. And so a Rocket Chip has been designed for tape-outs in Berkeley for ASIC. And so these things like these caches or like these shift registers, you'd have a lot of wiring that was like fine on an SoC, and then people got upset when we went to an FPGA. And so even though you could have a very small data cache, it may not be as efficient as what people wanted. Now, I don't know if Sci5 has fixed that or changed that at all.
We have not really put a lot of effort into making FPGA optimized designs. The designs Rocket Chip produces are mappable to an FPGA, but we usually are using that for ASIC prototyping. So we're looking for, you know, like the functional correctness of the design, and FPGAs are great at prototyping that and, you know, running for really long, you know, instruction traces. But I think there's probably a fair amount of low-hanging fruit even that could be squeezed out of trying to figure out how to make it more FPGA optimized. I do think what you start running into is how much of that involves changing the design itself versus how much of that involves, you know, mucking around with Fertile to get it to issue Verilog pragmas so that your FPGA tool puts it in BRAMs instead of, you know, LUTRAM or whatever, right? And so, like, that kind of tuning is something that would be a good contribution from the community.
So I have a question.
Yeah.
So is there a limit on the number of levels of caches that you support, or is it only the first level? Or?
Right. So at the moment, the stuff available in Rocket Chip basically only supports the first level caches and connects them with the broadcast hub. Sci5, we've been developing a composable cache IP block that would let you nest caches hierarchically, and we've used that in some of our designs. That is not currently open source, but probably will be within the next 6 months to a year.
So I have another question.
Sure.
So there are multiple components, like you have the NOC and everything. So can we replace it with some custom components, again, from the FPGA side? So
Yeah.
Is it?
Yeah, so the current knock is pretty simplistic. I'll get into this a little bit more later. There's actually sort of several buses that, at the moment, it's kind of a hierarchical crossbar where there's several crossbars that you can attach things to, sort of on the like kind of master and slave side. And the implementation the default implementation is this all-to-all crossbar. But there's a pretty clear spot in the code where you could be like, I don't want that, I want something else instead. And there was a there was an LBNL project that was looking at inserting a knock generator. I don't actually know what the current status of that is, but I could find you a link for that. Deprecated. It is deprecated, but it might still be worth looking at to see like what they were trying to do.
It's a good project. It's just not in Chisel 3 anymore.
Yeah. So there was a fair amount of stuff going back to that timeline picture. Rocket Chip has made the transition from Chisel 2 to Chisel 3, but not all of the projects in the more historical ecosystem also made that transition. Let's do Bora first, and then you.
A couple of things. So regarding the FPGAs, there is actually a stub at the moment for a Perl transformation. Actually, it's a hammer.
Oh yeah, there's that poster.
The hammer is a physically aware tool or a set of scripts that will take your Chisel output and map it into either the ASIC or an FPGA. The FPGA is much leaner than the ASIC path, but it is there and it works for, we know one board, ZC706. It's a fairly beefy board. If anybody, you can try to replicate that and try it out on less expensive boards. If anybody is interested in trying that out. So that is one thing. There is a stub of a project that is a working path that has been PR'd relatively recently, and you can build up on that. I have a second question.
Sure.
Is cache coherence in the open source?
Yeah.
It is?
Yeah. Yeah. What's not what Rocket Chips comes with is a basically a broadcast hub that uses like broadcast-based snoop mechanism to achieve cache coherence between either master ports coming into the system and any L1 caches that are included, and potentially any accelerators that have been added that have caches as well. So that's built in out of the box. What's not included right now is a composable cache that can be nested more deeply. Yes.
So I'd love to hear more about this composable cache. That sounds really interesting, but we knew that all that.
Yeah.
But what I wanted to ask was, who is the customer of Rocket Chip? There's a lot of different people that you could be targeting it towards. Who is like the main customer, and like who are the stakeholders?
Yeah. Okay. That's a good question. So, I think the customers, to my mind, are people who the primary. I'm not saying. I think people are now trying to take it in more directions, right?
I mean, there's a lot of different ways that it could be.
And I think it's intentionally designed to be a lot of the tools and the libraries that make it up are really designed to be as open-ended as possible, right? And so I think some of the things related to like parameterization or configuration have almost those are just projects that we found useful when we were trying to describe a certain set of chip designs. And I'd say the set of designs that we've used it for successfully range from, so Sci5 has produced like microcontroller chips using Rocket Chip. And so that's definitely on the smaller end of the spectrum. Scratch pad memory, single core, no floating point unit, right? Intended for some embedded application. And then both Berkeley and Sci5 have produced multi-core chips with virtual memory, with floating point units, with additional accelerators. And Sci5 has taped out a 5-core chip. I'm actually not sure what Berkeley's current core count tape out record is, but it's probably 4-ish. I don't know. Did someone do 8? Yeah. Yeah. Okay. So Eagles got 8. So I'd say like cache coherent multi-core SoC. For ASICs is sort of that's like the heart. That's the heart, and then you can try and take it in a microcontroller direction. You can try to take it in an FPGA targeted direction.
But that isn't like the main.
That's I think that, those are just the less well trodden paths so far. Yeah, I think Chris Celio, who's in the back, is the primary developer of Boom, which is the out-of-order superscaler that kind of slots into a Rocket Chip tile socket, and so that's another direction of kind of turning up the heat in terms of like size of design or like performance metric that you could go after, kind of using this as a baseline.
Yeah.
So,
kind of where the question was coming from was more like on the research to FPGA prototyping to ASIC spectrum.
Yeah.
But
I mean, initially it was very research focused, but with a big emphasis on doing test chips, right? Now I'd say the most active area of research, while test chips continue to be made, there's also a lot of emphasis on doing, there was the Midas talk yesterday, right? And, FireSim is this, like cloud FPGA compute environment, right? And so there's been, I think the active research areas are pushing things more in that direction. Meanwhile, the commercial interests, i.e. Sci5 in particular, but also some other companies, have been taking it in a like, Sci5 at the moment is producing cores that are mostly designed to map pretty well onto ARM's offerings. So we're basically, for the moment, kind of competing with them in this IP offering space. And we've covered, I think, something like 80% of their offered designs are now basically an equivalent thing is generatable from a Rocket Chip based ecosystem. And again, we've added more stuff to it that we haven't open sourced yet. But if you pick an ARM processor, you can basically, there's sort of a mapping back to a Rocket Chip-ish configuration. Okay, so I think in terms of orienting yourself, it'll be good to give an overview of the different packages that make up Rocket Chip. A package specifically is like a Scala concept and is just a way of organizing your source code. But I think in terms of how it breaks down the functionality, it's useful to talk about. And I think there's really Rocket Chip really has two sort of flavors of packages in it. There's what I would call like utility packages, which are there to sort of make software, help you out in your programming experience. And then there are RTL packages, or hardware description packages that are actually providing a specific generator to make some kind of actual hardware block. So make a cache generator, make an interconnect, make a processor pipeline. Oh, right. Okay, I forgot about this. So one other thing to note when working with Rocket Chip is that there's a fair number of Git submodules. So Git submodules are basically a way that you can track an external dependency that you want to be able to be on the bleeding edge of. So you don't want to necessarily have to wait for stable releases. You just want to be able to point at a specific Git hash and be like, that's what I'm using right now. So for a bunch of these projects, that haven't necessarily had, that either have been changing very rapidly, or we've been using Rocket Chip to find bugs in, or they haven't had a stable release schedule. Submodules have been a way for us to kind of stay on the bleeding edge of like, oh, there was a bug fix to Chisel. Like, let's get that right away. So this is just a current summary of them. The downside to submodules is that they're kind of annoying to work with. They're sort of a bolt-on addition to Git, and it's really easy to kind of cross yourself up with like which one's pointing at what when. So I kind of hate them, but they're also kind of useful. Anyway, I just mention it because it's something that you have to deal with. You know, it's in the README as well. But so all of these I think are pretty close to the point where we might be able to get rid of them. So Chisel and Fertile both now have actual like regular release cadences that are pretty quick. And as they've matured as tools, it's become pretty rare to find a Chisel bug, like unless it's a major new feature. So I think those we could maybe start just depending on the published jars of those tools. HardFloat supplies the hardware floating point implementation, and it's still used a lot, but it isn't updated very often. So that one I think we could probably, I just looked and it was a year since it last had a change. So that one we could probably publish to Maven as a published release and then just depend on that rather than having the submodule. RISC-V tools, now that the software compiler has been upstreamed into mainline GCC, you could just check out a version of, you could actually get a GCC release in, apt-get even it. So it's another one I think we could drop. And then Torture is basically a randomized instruction stream generator. It's designed to stress out processor pipelines. That project I don't think really has an active maintainer right now, so it's been languishing a bit, and we aren't actually using it for the Rocket Chip regressions. So, yeah, I don't know. That's as far as community involvement goes. That's a project in search of an owner at the moment. Yeah. So I mentioned these because these are all dependencies that Rocket Chip needs in order to function. Other dependencies are you need to have a JVM because Scala, which Chisel is built on, runs in the JVM. But other than that, I don't think Rocket Chip introduces any extra additional external Scala dependencies other than what you need to get Chisel to work.
Question.
Yes.
Do you have a Docker image or something that has all this set up?
Not an up-to-date one. Yeah, there was a period where I think you should Google around because various people have made them at various times. I also made my own at one point when we were trying to use it for Travis testing. Yeah, that's just something where I guess I haven't felt like there's been enough pain of people getting it set up. Well, there is some pain of people getting it set up, but it really has more to do with the tool chain. Like, in terms of people are like, I'm trying to work on this project, I want a 32-bit processor, I need a 32-bit tool chain, and so now you're like making a cross compiler and something went wrong, and so we get a fair number of issues related to that, and so maybe I think having Docker images with RISC-V tool chains in them would maybe be useful. The Rocket Chip stuff, SBT, which is the Scala build tool, just kind of takes care of most of it for you.
It is on Sonatype.
Yeah, but how old is it?
A few weeks old.
Oh, okay, great.
And I think it's somebody needs to check, but it's supposed to be continuously updated.
Oh, okay, cool. Is that?
I don't know how to use it, but
yeah.
It's supposedly there.
Okay.
And it's free as long as it is open source.
Yeah. Cool.
It's like I don't know who has used that.
Yeah. Okay. Okay, so these are like external dependencies that Rocket Chip depends on. Within Rocket Chip itself, as I was saying, there's kind of two subsets of packages. So the first set that I'm going to talk about are these utility libraries. So when I say utility library, what I mean is it doesn't really actually generate any hardware itself, like it doesn't describe any hardware. It is just something that is used in the process of configuration or describing the chip. It's basically used. These are packages that are used by the actual hardware generation packages, if that makes sense. So just to talk, and so these packages they're mostly Scala with maybe a little bit of Chisel in them. This is kind of like exploring exploiting the fact that Chisel is embedded in Scala, right? So what that means is you can use Chisel to describe some particular circuit, but you can also use any Scala library you want in describing your design. So, for example, the config package is basically a library for describing configuration parameters, basically turning knobs that change how the chip behaves. So that's a purely Scala library. We wrote it to describe these chip designs, but there's nothing about it has really anything to do with Chisel per se. It's just a way that we found convenient for expressing configuration options. And I'll talk more about some of the specifics of its behavior later, but just to give you a flavor. So diplomacy is another example. Diplomacy is kind of an extension of Chisel that allows you to negotiate parameters between a set of components that you're connecting to a shared interconnect. And it basically lets you do that negotiation before you start generating any hardware. So you can decide whether the design that you're trying to create is viable before you even begin to emit hardware. So again, if you open that package and look around at that code, it's mostly Scala code. There's almost, the only Chisel code in there, I think, is the fact that it passes around bundles, right? And even that's like kind of a type parameterized thing. So you could theoretically rip it out and use it for some other purpose. Similarly, the reg mapper package is this utility that allows you to describe memory mapped registers, and then it sort of works with Chisel to emit the actual RTL that turns those register descriptions into actual registers that are embedded in your design and connected to a bus.
So I have a question on the diplomacy part.
Sure.
So does it look only for the functional correctness for the okay, this is not valid, or does it look at this might be the bottleneck?
So far we've used it mostly for functional correctness. I do think you could do optimization. You could use the data structure it creates to do optimization, some kind of more performance or resource-based optimization. At the moment, really all we do with it is if we can determine use it to determine some property about the system, a lot of the time that can save you from generating hardware that you don't need. So for example, if you create a system that if you have a subcomponent, a subsystem where there's no coherency, there's no, nothing is able to cache anything, so there's no coherency traffic exchanged, that lets you save on the interconnect channels that would normally send those messages. Now you know that you don't have to generate those. So we'll sort of use it to improve quality of results, but at the moment it doesn't really do any, performance tuning directly. I can spend some time talking about diplomacy in more detail later. I think that's a good topic to get into a bit more. Okay, just to finish these out real quick. So the system package is where the Scala. So when you are running Rocket Chip, you want to create a design. So there's actually a Scala application that runs in the JVM that when you run it, it causes Fertile to be emitted, right? And so the system package is where that Scala application lives. The unit test package has this framework for generating synthesizable hardware unit tests and basically spitting out a bunch of them and then running them and collecting information about whether they succeeded or not. It's basically slightly different from how the Chisel testers stuff works. And then the util package has a bunch of stuff for doing like file I/O or like generating metadata if you want to describe something about the design. While you're elaborating it, you can collect that information and dump it out to a file there. Okay, switching to so those were the utility packages that are kind of there to be helpful. And then there's a bunch of packages that mostly contain actual hardware IP. Now again, these are all generators, right? So they're all generating different pieces of hardware. So the AMBA package, for example, has Chisel descriptions of AMBA buses, right, as bundles of wires. And then it also has a bunch of IP for generating AMBA traffic, having memory connected to an AMBA bus, that kind of thing. The devices package has a bunch of basically memory map peripheral devices, RAMs, ROMs, forget at the moment what else is in there. A lot of the devices have actually been moved out into other repositories as well. So this is an area where I think Rocket Chip's extensibility kind of shines. It's very easy to go in and be like, I have this new peripheral that I would like to add that speaks some other I/O protocol. And so that package has has examples of those. Ground test is another fuzzing traffic generator thing, but again, it's synthesizable. So we do a lot of testing based on having synthesizable hardware fuzzers that we then hook up to other parts of the system and then run run a simulation that has both the DUT and the fuzzer in one hardware design. The interrupt package is an implementation of having interrupts, right? That's like when you're trying to compose an SoC, one thing you have to manage is a lot of these devices might want to raise interrupts and notify the processor that something has happened. So the interrupt package provides a way, a way to express that. JTAG is JTAG debug interfaces. So the Rocket package is the sort of like original core, the 5-stage pipeline. It's also got the L1 instruction and data caches in there. It's got the floating point unit in there. And it has an interface for adding a ROC accelerator, which is basically like a sort of custom coprocessor. It's a slot to add a custom coprocessor. Sky is another custom instruction interface. So rather than having a sort of decoupled coprocessor, Sky is like a single cycle custom instruction. So it takes in inputs from the register file and produces an output that's going back to the register file in one cycle. So those are kind of two spots where you can kind of extend the design by extend the processor part of the design by adding more elements. So the subsystem package is what really makes use of a bunch of these other ones to kind of start tying everything together. So it basically provides some common attachment points where you can say, hey, here's where I want to hook up this additional processor. Here's where I want to hook up this additional peripheral. The tile package, so a tile is basically the unit of replication in a multi-core, many-core design. It's getting tiled across the design. Usually what we put in a tile is a processor pipeline, a ROC coprocessor, maybe an FPU, and then some combination of caches, L1 caches. And then that unit is what will replicate in a multi-core design. Okay, and then the tiling package is basically So as part of my thesis and then sort of following onto it at Sci5, we've developed our own shared memory bus protocol. And so that's the bus that we use the most internally. It supports different cache coherence policies, and yeah, I'll talk more about that later. But it's basically sort of the equivalent of the AMBA package, just the the Rocket Chip or Sci5 flavor rather than the ARM flavor. And then there's the utility package. Also has a bunch of hardware stuff in it, so like ECC codes, arbiters, functions to generate random numbers. Yeah, there's all kinds of stuff in there. Okay, so thank you for bearing with me through that long list, but I think it's good to sort of get the lay of the land. Any questions about that part? Okay, so next I'm going to talk about some APIs that I think are interesting or that you will almost certainly encounter if you try to use it. I think depending on interest level, we can spend an arbitrary amount of time on any one of these and or go look at some code that's actually using it. So definitely feel free to be like, I want to look at this one more, because otherwise I'm just going to kind of cycle through them to give you an overview, and then we can always sort of circle back to do a deeper dive on any particular one. Huh. All right. Okay. So this is from the config package. So as you recall, the config package is basically there to configure a particular design. So this is how we take in user requirements and inject them into the generator, right? So you have, I think the right way to think about this is we have all these different generators, right? They all have these knobs that they're exposing that can be tuned, and you need some way to configure all of them. Okay, and so the fundamental abstraction we use here is this thing called a view. And really, I think the easiest way to think about it is it's a key value store or hash map, but with this one special property. And the special property is that when you look up a particular key to get its value, that value can be based on further lookups of other keys. So the reason why that's powerful is because when somewhere in the design I want to look up the value of some parameter, that parameter can be derived based on looking up other parameters. The other cool thing about it is that you can override values as you pass this object through the hierarchy of generators, right? So you can give you can give it to the subsystem generator, which could modify some of the keys or values before passing it off to the tile generators or passing it off to the knock generator. Yeah, if you look in the config library, you'll see this class called a view, and then there's actually two sort of subclasses of it. Historically, these were actually two different libraries that we were working on. The configs one was for top-level configuration, and the parameters was more for what I was just talking about, like passing it through the design to different generators. As we continued working on it, we actually figured out that they were really the same thing. So at this point, they're basically just two slightly different APIs that are a shim over this view thing. It would be nice to clean that up at some point, but I don't know if it's ever going away at this point. That would be a lot of code to change. Yeah, I think I'm not going to talk about the specific API for altering the views right now, but that's something that we could put a pin in that. That's something we could talk more about. Whoops. The configs one is what you're more likely to run into as a initial user, because if you want to configure your chip, you're going to have to go in and change some of these things. So looking at this little example right here, so in terms of how these views work, there are keys and values that you can look up. So in this case here is what, when you do a lookup, you're basically matching on these cases, looking for a certain key. So the key in this case is this number of external interrupts. And it returns a value, which is an integer. And so what's happening here is this person is making an instance of this class called config. They're parameterizing it with this number of external interrupts, which this itself is parameterized. And what that gives them is this sort of config class that sets this key to that integer. And so while this example is a bit trivial, you can imagine how you can build up these pretty complicated configuration objects by combining these config classes with each other. So in this case, what's happening is they're taking some existing configuration here on the right that presumably already has a bunch of keys and values set in it, and then they're modifying it by composing it with this other config that changes the number of interrupts that the design has. So my config here, sorry, do you guys see the, yeah, okay. So my config would be a default small config, but with the number of external interrupts set to 16. So if you look around in Rocket Chip, there's a couple of files that define these configuration objects that provide named settings. And then there's sort of an additional set that kind of combine those partial configs into complete configurations that supply all the key value pairs needed to generate a particular design. Okay, did that make any sense?
So that's where that kind of nested key value hierarchy comes into play there.
Yeah, so what's happening in this case is, what's happening here is, so Scala has this notion of a partial function, which is a function that is only defined for some values. And in this case, what the places where the function is defined are the keys you've supplied. So if I look up a key, Scala will go and try to match that key to something in this partial function. And so it'll go through and it'll evaluate a bunch of case statements and be like, does this match, does this match, does this match, does this match, until it finds the key that does match, right? So what's happening in this case is, even if this default small config had a case and external interrupts set to 1 or whatever, because we've composed it in this way, when I look up an external interrupts in my config, I'm going to find this case first. And so that will become the value that I get. So part of it is composing them by ensuring that the sort of frontmost one matches first. And then what this example doesn't include is, rather than saying I want number of external interrupts to be this particular integer that I told you, you could instead use these cite up in here functions to actually look up a different parameter. So I could say, I actually want number of external interrupts to be equal to looking up some other key, like what is the number of plick interrupts that this configuration supports. So it allows you both to overlay keys to sort of replace what was there previously, and it allows you to have keys that look up other keys. And you can combine both of those things together to do some stuff that is probably slightly too fancy. is the summary there. But in terms of the initial use, I think yeah, let's leave it there for now, and we could go look at some actual code examples if people want to in a bit. Okay, so diplomacy is a pretty deep topic because it's how we interconnect basically all of the generators in the chip at this point. But just to give you a quick flavor, the fundamental thing it does is it adds an additional step to Chisel. So Chisel, normally you're creating modules, which are Scala classes, and the constructor of the Scala class contains all the hardware that the module contains. It contains the Chisel, wires, reges, and muxes, right? And the way you create your module hierarchy is when you're making one module, you can say, hey, actually, I want to make another module, right? And you can say, you know, my child module is this. And then now you're in that module's constructor, and you're building hardware inside that module, right? So there's this actual, you know, the call stack of these module constructors becomes the module hierarchy that you create. And that all kind of happens in one straight line pass. That's sort of fine. Basically, when we designed Chisel, we thought that was fine. But it turns out the problem with it is that it means if you want the generators to generate based on what other things are included in the design, you have to do a lot of pre-computation in config land, in that config library I was just talking about. You have to do a lot of like keys looking up other keys, how many of this thing did I have where, and you're trying to like pre-compute it all so that you can then have it sort of ready to go when you go and construct all these modules. So that's the backstory. What diplomacy does is it adds a whole extra pass to the whole process, where first I go through the module hierarchy and I describe metadata about the module and how it's connected to the rest of the system. Then I run a computation over that connectivity graph, and I do a bunch of checking on it. And the checking is, you know, if some master requires that it can perform this sort of operation on the bus, and there's no slave that can support that operation, you should error. Or if the bus thinks that it is 64 bits wide, and the slave thinks that it is 32 bits wide, and you didn't include something that adjusts the width, well, that's a misconfiguration and you should fail. So there's this negotiation phase that you go through, and everybody has to agree, hey, this design we're about to generate is correct. And if they all agree, okay, now we're going to go and we're going to actually do the normal Chisel elaboration of hardware. But that becomes a sort of second phase. And so what you'll see when you look at the code base is lazy modules are this extra wrapper around Chisel modules. And the lazy part is setting up this connectivity graph and sort of describing what is going to happen when the lazy module is finally resolved. And so the lazy module implementation is the actual Chisel implementation of the module. So when you're looking through the code base, what you'll see a lot of lazy modules, and they'll all have a matching lazy module implementation. All the Chisel code is in the lazy module implementation. What's in the lazy module is Scala code that is this diplomacy, that is using these diplomacy constructs to describe the connectivity of the chip. So how do we describe that connectivity? It's a graph, and specifically it's a directed acyclic graph of nodes that are connected to each other with edges. And so nodes are basically, a lazy module can have multiple nodes, and when and so each node is sort of a point at which traffic is going to be generated. Some kind of interconnectivity traffic is going to be generated. It could be tile link traffic, AMBA traffic, it could be an interrupt, but some signal is being sent to the rest of the design. Okay, and so a node can have edges. An edge is like what it's connected to. And specifically what it gives you is a view of the graph from that node. So like if I'm a master and I have an edge connecting me to the shared memory bus, what I can do with that edge is I can say, hey, like what addresses do I see? Or hey, like what permissions do I have on these addresses? Or hey, is there FIFO message delivery between me and that guy? These are all the kinds of questions that you can compute using this graph. And then you can use that to change the hardware that you're going to emit. Okay, I think that's a good high-level summary. We can definitely talk about this in more detail if people are interested. And then these, if you're looking, again, focusing on what you'll see in the code base, in the lazy modules, you will see either nodes or these connectivity operators, which are basically describing edges between the nodes. And so they basically are saying this is connected to that. The star is probably not worth getting into right now, but it's basically the cardinality of like how many things are connected on each side. Anyway, the real point is nodes and edges. Any questions about it at that level?
So for the connectivity, so far we support point-to-point connection. Do we support one-point connect to multiple?
Yeah. So you can have one point connected to. You can have one node that has an edge that connects it to multiple other nodes. It's a multi-graph specifically. You can also so let's say a master connects to a crossbar, and then the crossbar has many slaves, right? So if you think about the shape of that graph, there's like one connection to a node, and then that node has many edges coming out of it, right? And actually, I think I have a picture. Yeah. Wow. Great. Okay. So this is an actual small. So one of the outputs that Diplomacy creates is this output format called GraphML, which you can then plot. And so if you are using Rocket Chip and you want to look at a design that you've made, this is actually a pretty fun way of debugging it or making sure that doing validation, basically, that you built the right thing. So what are we looking at when we look at this thing? So the yellow dots are nodes. So those are points at which some amount of hardware is being generated based on the graph. So for example, the iCache and the dcache, right? They have little state machines inside them that send tile link bus traffic, right? And they have some requirements that they enforce. So like for example, if there's no cacheable memory and the dcache is not configured to be a scratch pad, that's probably bad. Like that, that's a policy decision on our part, but we've basically said, hey, we should error out in that case because you probably screwed something up. Like you probably didn't mean to have a cache that can't cache anything. Like that just seems bad. So in order to do that check, we have to be able to look at the rest of the system. So the connectivity here, so the dcache and the iCache are connected to a bus inside the tile. And the boxes here are the module boundaries, right? So this graph crosses through module boundaries. And the way to think about it is every time an edge crosses a module boundary, Diplomacy will make a port in that module that will carry that traffic, right, in the actual hardware that gets emitted. So going back to the connectivity question, so we have some masters here connected to a crossbar. It has only a single port out of the tile, or out of the core to the tile. There's some adapters, and then it gets connected to this big system bus crossbar, right? Tile, right. Okay, and so then on the other side over here, you can see there's a bunch of peripheral slave devices. So these are basically things that have memory mapped registers in them that are visible on the bus and can be read and written using memory mapped I/O loads and stores. So the way that we describe that connectivity is they basically have a single slave port coming in, and they're connected to some bus over here. And you can see that they sort of each have one connection going out. They all need some support in order for basically, because they only support having a single register read or written, but this bus architecture supports multi-beat transactions, right? You can have arbitrarily sized stores, loads or stores trying to access big regions of memory. So you need some adapter that's going to break that up for you and turn it into something that their controller understands. So that's like, for example, that's what this fragmenter node here is doing, is it's there to break up a burst into individual beats. If you didn't have this, then you would get an error because at some point in the checking process here, these guys would realize that they are about to be subject to traffic that they can't support. And so that's a kind of like, that would be an error. That would be like a diplomacy negotiation time error. All right, and so then the buses can be connected to each other. You can insert more adapters in between them. So for example, these guys don't support the tile-link atomic transactions directly. Instead, this adapter over here provides support for them by turning them into a read, modify, write operation. So that's another example of like, rather than having complexity in these slave devices to support this additional bus transaction, you can instead say, I don't support that, and then leave it up to the person who's connecting up the entire SoC to insert this adapter that now they are supported. So now when the tile looks in this direction, okay, so that was peripherals. Okay, and we also can have, we can convert to other bus protocol types. So this example rocket system actually speaks AXI on the endpoints. And so we actually have a tile link to AXI for converter that we interpose there in order to be able, and you can maybe barely see that the black here, which is a tile link, changes to blue, which is an AXI connection. And then we have a bunch of AXI things that, these are all kind of shaping the traffic that goes to this port. So I think one of these, for example, is actually an AXI light port, so it doesn't support bursts. So again, it needs something to break the bursts up so that it only issues single beats. Similarly, you can have AXI to tile link coming in on the master side. This doesn't have the rest of the animation. Okay. Oh well.
How does memory mapping happen?
Yeah. So there's another library. So diplomacy has a way to say, I'm a slave node, and I own these addresses.
Specific in the whole address space, or in some?
So yeah, in the way it's encoded right now is a slave device is configured with addresses that it usually gets by doing a key lookup in that configuration thing I was just talking about. So it does a lookup there, and it says, what are my addresses? What did the user say my addresses are? Now it knows the addresses. Then when that lazy module constructor is running, it makes a diplomatic node, and it says, here are my addresses. I claim these. And everybody does that, and it feeds their node, creates their node claiming some addresses. Then when you connect everything together with these edges, you do one of the things that you do is address resolution, right? And you basically make sure that at any point in this graph, there's a unique path to get to that address. That lets you generate the address decoder logic that goes into the crossbars or whatever your interconnect fabric looks like. And if you ever try to create a bus that doesn't know how to route an address, or because two people have claimed it and now it doesn't know where it should go, you can error out. And so that's another way that diplomacy can detect misconfigurations before you've even emitted any hardware, because that was an unworkable design.
So this architecture though assumes that you know what all the registers you want to have, and you have to actually put an address in. You can't do instantiate everything, find out what addresses could happen, come back with an address map. That makes sense. That simplifies the design. So that's not.
Yeah, that's not really currently supported. I think you could. That's something that we could consider adding. I think in that you could have. So one thing you could do is you could have the thing that found conflicting addresses could move one of them, and then basically to the upstream thing, I'm going to say lie, but that sounds too negative. It will say, hey, I have this at this address and this at that address, and sort of send that. So when the tile looks in this direction, it might see things that were conflicting as offset from each other. However, what the policy is for moving addresses around, I don't know. And in my experience with at least our like Sci-Fi customers who are coming in and trying to configure their chip, they usually have a specific address map in mind, possibly based on their legacy software, that they want us to implement for them, and they don't want it scooting around. So that not theoretically possible, not currently implemented.
Well, we don't use this concept yet, but our thing generates a memory map into both our Python and our C++ code so that we can write whatever, but everything's to a name, so we don't actually care what the address map is.
I see.
And so what happens is our current knock generator, whatever you want to call it, automatically generates addresses all over the place.
It picks.
And then it picks it so that it has the best route to keep these addresses, so you don't have to have these huge address buses going to a peripheral. You can keep them small.
Yeah, this will we try to generate the minimum amount of decode logic that's needed in order to compute where the address should go. And if you do a good job of picking addresses, then we'll do the right thing.
Sure.
But it doesn't quite have that level of, I think you could change it such that they only say what size they are, and I want something upstream from me to pick for me. I think that would be it would be possible to do that. Maybe not trivial, but possible.
Yeah, well, then we have to auto-generate all the wrapper code for our
Yeah.
register access layer.
I think the other thing is the easiest thing to do would be to do the resolution as a pre-computation and then feed it into our thing. But I think you would also bake that into basically the upstream nodes would have to be smart enough to be able to be like, oh, this is like here's how I'm gonna juggle it. But a lot of these adapters do that kind of transformation where below me it was this width, above me it's that width. I'm changing the width. And so when the tile looks, from left to right here, it's going to see a view of the memory system that, has had all of these things applied to it. Okay, I think I sort of already talked about this. So that graph, all the nodes in that graph are basically doing a simple transformation, a single kind of transformation on the data that's flowing through them. So the width widget, for example, is adjusting the data path width. That's the only thing it does, right? So the idea is that most of these things are stateless and combinational. So it's easy to compose them, a bunch of them together, into some kind of bus transformation that happens in a single cycle. You can also add buffering stages to it somewhat arbitrarily, depending on what protocol you're talking about.
Is this manually inserted, or is it something that Diplomacy figures out?
Yes, at the moment it is manually inserted. However, automatically doing it is a to-do ticket item and something we're interested in. In order to do that, you have to add some notion of capacity to the edges, and then have some notion of distance in terms of I think the challenge is how do you say how many, you have to have some way of driving the search, right? So you have to be either able to say, I demand that the latency between endpoint A and endpoint B is this, or I am willing to spend up to this many resources on buffers between A and B, and then do the best you can with that. And we just haven't really figured out what I don't know. That's the next level of complexity, I think. At the moment, we still require manual buffering. not to get too much into the specifics of the tiling protocol at this point, but all of its channels are decoupled, which makes it very easy to insert these stages. And the semantics are such that you can, a lot of times you can kind of mash a bunch of these adapters into something that happens in a single cycle. The reason why I like this design pattern is because it makes it sort of easy to check that each of these adapters does the right thing individually. So we have unit tests of each adapter for like a wide set of parameters, right? Like, so bus widths, you know, converting between many possible bus widths. So we verified that independently, and then we are confident that composing them will achieve, you know, the total desired effect, right? Whatever you're trying to change about the data as it flows through these nodes will be accomplished, but that you're doing it, basically I think it's easier to get compositional correctness than making one mega circuit that, you know, written by hand, I mean, like one module that does all of these things and then making up, you know, having slightly different versions of it all handwritten. Instead, we have these sort of like very thin adapters that we compose together. How am I doing on time? Am I super over? Yes. Great. Okay. Well, let's see whether there's. Sorry, guys. You know, okay. Let me do a real quick thing about this section, just because I think this is pretty useful. So there are a bunch of other repos that you can add on to Rocket Chip that make it, you know, have more features. So one is this Sci5 blocks repo. So there's a lot of stuff in there. It's all these like memory mapped I/O controllers, GPIO, SPI, I2C, etc. So those are all things that we developed, and they just plug into Rocket Chip automatically, and they're free to use. That's pretty cool. Another one is, so NVIDIA released their DLA inference engine. We took it and wrapped it up in Chisel and gave it diplomatic nodes at its edges. And so then now you can just sort of, again, throw it into the SoC, connect it to the bus somewhere, and incorporate that.
It is not in Chisel.
No, so, but the point I'm making is the DLA block itself is in Verilog. We black boxed the Verilog, and then we wrote some Chisel around it that converts from tile link to AXI, and, you know, makes some, you know, and is like, hey, I'm an AXI, you know, I'm a master port that generates this kind of traffic based on the specification of the block. And so then now it's sort of just, you can just drop it into any Rocket Chip system and hook it up to the bus. So it's like the NVIDIA Verilog wrapped up in some Sci5 diplomacy. The FPGA shells repo is cool for taking one of these Rocket Chip designs and mapping it to an FPGA. You can actually take the same design and map it to multiple FPGAs. There's this kind of like neat abstraction layer there that I don't have time to get into, but cool stuff. There's like 4 or 5 different FPGAs that you can map things to. Freedom is our kind of mega repository where we combine all those different things into some example chips, including stuff that can be mapped to FPGAs. So that's a free Sci5 offering. And then there's this Berkeley project template, which is a lot like Freedom, but much, much simpler. So that's good for more of like, if you're more interested in like getting started and playing around with like adding a device or adding a coprocessor, they have some nice examples, and it's just much simpler to work with than Freedom, which is kind of a big, hefty thing, but will get you a cool design out of the box. So it kind of depends whether you're more interested in like, I want to take this and run with it on an FPGA, or I want to fiddle around with writing my own RTL. Okay. Yeah, we rewrote it all to be diplomatic. We're adding lots of features to diplomacy. I'd say that's a much more active area of development than Chisel itself is right now, at least for Sci5. Tile link, we're continuing to improve. And then there's going to be more wrapped IP similar to the NVDLA thing, more FPGA targets, and then we'll probably also be releasing some of our own custom accelerators. And If anybody is working on projects that are doing any of these things, and I didn't mention it in this recent set of slides, you should let me know about it, because we would like to help promote all the people using this ecosystem. And also, Sci5 is hiring, so if you want to get to ask me more questions about this, sending me a job application is a great way. All right, thank you guys very much.